All right, ITS538, 16-week format, week three, modeling data using the entity relationship diagram. So um, this week, the the point, the mission is to start looking at data and diagramming it. As they say, a picture says 1,000 words. So we'll go over this diagramming this data in this particular format. A lot of it's UML. There are quite a few different formats. It really depends on what company you wind up working for and their modeling tool. I'm used to modeling data like this using the ANSI standard that Workbench uses when Workbench, MySQL, generates can generate an EER, enhanced entity relationship diagram from the data using the constraints that are modeled within the data and the relationships that are modeled. And that's the format I'm used to using. So we'll go over this, and there's some good things to think about when it comes to modeling data and listening to your clients' data needs, and on the other side, how to sort of look at a database that's already in existence and kind of backwards modeling to the requirements um, that it fulfilled. So, good chapter. Make sure you read it completely. I think you'll need to know all this stuff. But anyway, yeah, entity relationship diagrams here. Um, so there's two approaches to this. I'm used to both. Historically, back in the day in my career, but I started out doing really more database design, where you understand the structure and format of the data. What how things are related, how you keep um, the data together, how you link things together, the constraints on the data, whether there's a range of values, or if you have to have maybe a lookup table like state codes. You don't want to just let somebody type in two letters for the state. So I'm used to modeling the data and getting the data right, because you can make an application design, the next main activity. You can design an application on top of that data to do anything you want it to do. Um, and that application may change. That application may be different for different people. But the core data requirements are 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 more long and are more enduring. So for this one, yeah, we're looking at the conceptual model of the database, conceptual database design. And you'll see the diagrams and the methodology in the chapter. You're modeling not just the data items, but you're modeling using verbs. You're modeling how they relate to each other. Like a person works in a department. Uh, so you model that works in using the ER diagram format for in this chapter, whereas you don't normally model that in a traditional entity relationship diagram. But this week we will. So yeah, database is all about the information. Applications are how that data gets entered, how it gets manipulated, how it gets queried. You can separate those two design activities. Okay, so let me put this in slideshow. Maybe make it a little bit bigger. Slideshow from current. Um, So this shows um, the phases of database design. So, you start with the mini world, the overarching problem domain, and then you immediately go down into a requirements analysis. That's its own discipline. That's its own thing. Business analysis and requirements, functional decomposition, all of that. You could make a career just out of that. But out of the requirements, you have functional requirements. What things do we need to do? What activities do our users take part in? And then there's the data requirements and the functional requirements. You go through functional analysis. You decompose. Who does what. How do they do it? How are those functions completed? Do we click on a button and make something happen? Some procedure? Is that procedure going to be automated? Are there going to be manual steps in it? All of those sorts of things are your functions. But on the data side, we get down to a conceptual schema, which isn't something that you could implement in the database. It just gets everything down on paper, what you want to store. And it's something in an initial design that you could take to the user, and then they can look at it and say, yeah, yeah, I understand. You explain to them the diagramming. It's pretty straightforward. And they go, yeah, yeah, yeah. Those are all the things I care about. Those are all the things that I work with. Um, so then you drop down into the logical design, which uh, you see there's a dotted line between DBMS specific and DBMS independent. The that logical mapping kind of spans those two. And then underneath that, you get down to the no kidding, the database creation and the code that does the application. And at the very bottom left-hand corner, you have application programs, which have both. They have the data that your users need to um, operate on and the applications that do those operations. Okay. And if you're not in IT, this is a view of everything we do. Um, okay, what we're doing this chapter is entity relationship diagram. It's very, I don't use this. Uh, uh, so I haven't worked with users in a long, 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 long time. But when I did, I used the EER diagram format. But there are large scale systems where you can store these conceptual issues as more as data, almost like flow charting programs and whatnot. And then unified modeling language, going back to the old Rational company 30 years ago. Um, Class diagrams, particularly the attributes of a class in object-oriented modeling, relate really well to an ER. But UML also includes the functions, the methods. So there you go. But we'll just work on a really high level conceptual diagram this chapter. So here's a scenario. Okay, so it goes through it in the book. We're going to create a database schema um, for a company database. So the company is broken into just like in most company, it's broken into departments, and that department we will uh, come to know it as an entity. Each department is an entity of its own. I mean, it's using English for a specific purpose, but these terms, most of them are all intuitive because they mimic what these things really are. So each department has a name, a department number. It's got a manager, um, and we want the date that the manager was hired. So That department can be located in several locations. So this is kind of English language of what a user would tell you. And if you have any experience in data at all, you can start to see how the requirement doesn't quite match anything that you could implement in data. So you need to get to the bottom of this conceptually first. So each department it has a project. So we're in all capital letters, right? So uh, project is another entity. So a project has a unique name, like a key field, a unique number, and a project has to be at a given location. So we can already start to see here that, a department can manage a number of projects. So a department manager is managing, ergo a number of projects. But a project has to have a lead department. Okay, that's page one. And now we're seeing employee. That's another entity. That's another thing, an entity relationship diagram. Um, and an entity generally is a noun, a person, place, or thing, generally. The database will store each employee's social security number, address, salary, sex, and birth date. Um, so these are user constraints, right? This is typically something people would throw out at you that have no idea how you design a database. So we just kind of go with it. So an employee has to work for one department, but maybe assigned to several projects. Okay. So the database needs to track at a weekly level um, a number of hours that an employee works on each project. And we need to be able to store the employee who is the employee's supervisor. So we're starting to look at thinking of maybe a parent-child relationship, which we can easily model in the database. And each employee may have a number of dependents. And again, a dependent isn't a company employee. Um, but they can have zero or more dependents. So we need to know um, who the employee is that is the sponsor of the dependent, and then we need their name, sex, birth date, and their relationship, spouse, child, mother, father, whatever. This would be very important in the sense of healthcare insurance. If you are tracking how many people are covered under someone's healthcare, you would need to know the some of the dependent information. And in the military, same way. That's where I grew up. Okay. So entities and attributes. Um, eh, Again, this is all very intuitive. We're just going to cover the required jargon. An entity is a thing, a person, a department, a car, a project, right? It's a thing. Um, an attribute is something that entity can have that describes them, right? So an entity would be person, an attribute would be name. Uh, Things have attributes. They have sizes and colors and uh, whatnot. So that's the difference between an entity and an attribute. Um, for example, you've got an employee, he's got an attribute of name. You've got a department, the name of the department is the research department. And you've got a project, and its name is Product X. Now, name may or may not be unique. Uh, um, the department name is probably going to be unique. You probably don't want to have two departments with the same name. So we're not looking at uniqueness yet. We're just looking at entities and their attributes. And you can have similar attributes. Um, you know, if you run a gym, you might log someone's weight. Well, you're also if if you serve food, you're also logging the weight of a serving of a smoothie or whatever. So they can have, entities can have similar attributes, but for that one entity, the attribute has to be specific to that entity. You could have products that have colors. You could have, um, I don't know, buildings that have different colors. So just because they each have a color doesn't mean it's stored in the same place. Um, so anyway, there you go. Attributes describe the entity when you start adding in the data. So the employee could have, name, social security number, address, sex, birth date, and you can have two employees that live in the same place. But you got to have something that will generally uniquely identify the entity. Before I forget, I'm going to say, do not ever use a real world unique identifier um, as the unique identifier in a database at the implementation level. Conceptually, you can do it, but when you go to implement, it's dangerous because that can change and screw up your whole database. So don't use social security number in a HR database, for example. Okay, so attributes describe an entity. An entity is a thing. That entity has attributes. Attributes don't have entities. Entities have attributes. So any specific entity. So you have an entity in general, like a person. A specific entity would be a specific person. A specific employee is going to have values associated with themselves that eventually can be determined to be a real world person. So you have to be a little bit careful. It's called personally identifiable information, PII, in the case of personnel data. So that is something to be aware of. So each attribute that describes that entity can have a value set, which is just the range of values or data type. So you can have, integer, and that can be further constrained, could be integers between 1 and 5. You can constrain that in your model, and you can constrain it at the database level. Could just be a string, could be a date. An enumerated type would be like um, MF, male, female. Um, if you wanted to have a pick list of uh, employee types, like manager, software engineer, job role, those sort of things that are enumerated categorical variables. So, um, yeah, entity attribute. A simple entity has one thing in its value, single atomic. Um, yeah, like social security number or sex. A composite attribute, you can go ahead and model it as a composite attribute. It's got more than one piece of information in that attribute, but it's safer to implement it everything as a simple attribute. You don't want to you don't want to store first, middle, and last name, for example, all in the same attribute or column or um, variable, um, because you might want to deal with them separately. But for modeling purposes at the conceptual level, you have simple and composite. And yeah, you can potentially have, a composite attribute inside of a composite attribute. And again, this is conceptual. Um, multi-valued entity, or I'm sorry, multi-valued attribute. Um, Sometimes that attribute can have more than one entry into it. Maybe you have 3 degrees. Um, it could be their car is blue and white. So you would put that in curly braces in the conceptual model. Of course, if like I said, if you're an experienced database developer, you're already thinking ahead to um, how you would model a many-to-many relationship like that. A lot of databases in reality make you pick a color, even if your car is absolutely 100, 50% blue, 50% white. They didn't want to go to the trouble to model that. So you have to pick a color. It's blue white. That's not one of the valid values. Uh, I'm joking. So, and yeah, composite multi-valued attributes, they can be nested. Although this is getting kind of into the weeds of modeling. But that's how they would be annotated. For example, if you have multiple previous degrees that you're going to store in the database, you would annotate in your diagram what attributes each of those previous degrees held. So it's almost like a previous degree starts to look like an entity with attributes, but it's not because it's attributed to each person. Okay. And this is, yeah, like I said, it's all in the textbook. Um, yeah, multiple previous degrees, and they have 4 subcomponents. Um, and address is another one. Generally speaking, yeah, conceptually, you model this composite attribute address, and you can kind of move on. But there's a standard format for addresses, and it gets to where geographic information systems have that broken out into specific, um, very specific uh, sub attributes. Um, the street number, a legal city, a legal state, zip. A street address can have the number, the street. It can be subdivided into apartment number. Um, and there are databases of legal addresses in the United States, so that you don't have to guess. You can make your user choose these attributes, which makes things a lot easier. It avoids errors a lot, especially if you're doing anything in e-commerce or delivery or uh, insurance assessment, anything like that. You're going to want to use a rigorous database of locations. Google has an enormous database of its own location IDs that have those attributes mapped out uniformly. uh, Entity types and key attributes. So, um, yeah, um, all your employee entities would be grouped together, and your projects would be grouped together, um, because they have similar attributes. Now, if you've done object-oriented programming, that sounds like a class, and you can have a subclass where you constrain that or even add attributes, and so you have a base class and subclasses. But for this one, we're just conceptually modeling. Um, the entities go together, um, but you will frequently, and I would say more often, much more often than not, you need a unique value. Each entity must have a unique value that is the key attribute. In database speak, we say it's the primary key of that entity. For example, social security number, for our government's sake, social security number is a unique identifier for you. Now, there are other unique identifiers. A driver's license number can only be issued to one person. So There are other unique identifiers. I would encourage you going forward to use a system generated primary key and leave real world fields like driver's license number or social security number, leave those as attributes. Don't make them the primary key. But it's going to depend on where you work and the constraints of that organization and how they've designed their database. So a key attribute may be composite. In database speak, that's a compound key. Vehicle tag numbers, your example. You've got you could have uh, two states issuing the same tag number, so you need the state and the tag number combined uh, as a composite key for that car. But each license plate, is only supposed to be on one car. But there are exceptions to that. There are places that will let you move maybe like a handicap tag from car to car. So yeah, that's not a clean example. So in our parlance, a key is underlined, a key attribute is underlined. If you've looked forward through the book, these diagrams are busier than they need to be. I guess maybe that's why I've never used them. So in uh, each entity type, person, will have a collection of entities stored in the database, and it's called an entity type or an entity collection. Heard it. I've never heard it called that. That would be a table, but conceptually, an entity set or an entity collection. Um, so we had three previous slide shows three car entity instances. Uh, I don't see that. I think it's in the book. I don't think it was in the slide. Um, the the car, yeah, refers to the entity type and entity set, but they don't have to be the exact same name. Again, this is high level conceptual. You don't implement in the design diagramming format that the book talks about. And yeah, the current state, that's the actual data that's in the database. We've talked about that. Um, So the value set of attributes, that's just the data type. That's just the legal range of values you could put it at. If it's, wide open, any integer value, then okay, fine. But it just has to be a value. You can't store a decimal number in there. Dates very often have a strict formatting mask. And at the database level, it's going to demand that you put dates in a certain format, but you can override that and deal with it at the application level if you need to. So yeah, a value set specifies the set of values associated with an attribute. It's just the legal values that any one thing like, hair color or name or birth date, what legal values they can take on. Very similar to data types. In fact, go ahead and think of it. You're going to see some mathematical notation in the book. To me, it's superfluous. I won't be looking for you to publish any of this sort of stuff. But yeah, you're welcome to look at that mathematical notation for setting and subsetting and whatnot. Um, so in a ER diagram, your entities, your main attributes, I mean your main things, people, project, department, are going to be in a rectangle, and each um, attribute of that entity is going to be out in an oval, which is why these things get so cluttered they're almost useless. Uh, if you've got something with, and you easily could have something with 100 attributes, you got 100 ovals cluttering up this diagram where it's a little cleaner in an enhanced entity relationship diagram or a traditional ANSI standard entity relationship diagram. And it's each attribute has it's an oval drawn with a line. Um, and then the keys are underlined. And if you can have um, you know, more than one value, it's in double ovals. And um, there's a cheat sheet for it in the book. And here you go. So a weak entity doesn't have any primary key, which is fraught with peril at an implementation level. But for conceptually, that's what it looks like. And then a diamond is a relationship. Ovals are attributes or columns. You underline a key attribute. Um, if a column or an attribute is going to be going to have more than one value in it, you draw two ovals. A composite attribute like address will be broken out into its own sub attributes. Uh, a derived attribute, that's something that you can pick up in your requirements analysis. People may think that it's something you would store. So they really, really, really want to see it on the diagram, but it's not. It's not something you would store. It's a derived attribute, as we see down here. That would be something like quantity on hand. In only rare circumstances do you store something that can be calculated or should be calculated in real time. You go ahead and just call that a derived attribute and you model it with a dashed oval. Um, this total participation refers to whether or not there can be nulls. Cardinality is whether or not you can have more than one. Like the cardinality between person and dependent would be one to many. Each employee can have many dependents, but each dependent has to have one employee that is their sponsor. So it's a one to many, one to n. Um, and then you can have a structural constraint where you start looking at ranges of values, either date ranges or integer ranges, those sorts of things. Constraints on the data. Oop. For example, we've got a car. There's a few examples on the of attributes on this diagram. It's going to have a model. It's going to have a year, but it might have more than one color. Colors in a double oval. It's going to have only one make. It's going to have a registration and a vehicle ID number or VIN, vehicle identification number. Um, but the registration, otherwise known as the license plate, uh, is going to have the state and the number. You can put those in the same column. You can, but it's safer to to break those out. But these are some good examples of how you would model a car entity. Car is in a rectangle. Car is an entity. Things in ovals are attributes of that entity. So you know, in English, we had our four main entities, and uh, our requirements also allowed us to list the attributes or describe the attributes, and they're in this diagram, just like you would think. Um, with the key locations, a department will have a unique name and a unique number. So within the scope of this entity called department, it's kind of redundant as far as being a primary key. But each project will have a number and a unique name. Again, kind of a duplicative key. You may have a project that you want to call in another location. You may want to reuse that project, but each one would have a unique number. So a way to identify it, or you could do a compound key. Anyway, and there's look at all these, this employee that's starting to get really busy with all those bubbles, all those ovals. So that's why I'm not such a huge fan of this conceptual format. To me, it takes up more room than it need be. You can model the same thing in a single rectangle um, with symbols next to the attribute instead of double bubbles and whatnot. But anyway, there you go. It's not complete because we have not represented the relationships. So we don't know how employees and projects are related. We don't know how departments and projects are related. Um, I mean, we do in the requirements, but we don't in the model. So we'll bring that in here, this next one. So there's three main points, three main concepts of the ER model, and that's to get the actual entities down, the nouns, um, and their uh, what they are, and then the attributes of those entities. But you also need the relationships and their relationship sets. So that's the next part. So, I mean, this is the whole reason a relational database exists, right? Is to automate the way these entities relate and track it and maintain it and enforce it. Um, uh, and not everything in your database will be related to something else in the database. You can have standalone, but it's pretty rare. Uh, so John Smith works on now on this slide, the relationship is in bold. The entity um, is not bolded in the on this slide. It should be. Let me see if I can fix that. Bugs me. These come from the book, right? If you all were watching this closely, intently, like I know you are, from current slide, project should is an entity. It should be all capitalized. So John Smith, employee John Smith, works on product X project, or Franklin Wong manages the research department. So manages is the relationship, works on, but it's also a verb. So, like I said, most entity relationship diagrams that you work with in industry do not model um, the relationship with actions like this. At least not the ones that you generate out of MySQL Workbench. Um, Relationships of the same type are grouped or typed into a relationship type. Uh, so yeah, works on is just for employees and projects. Manages is just for employees and departments. Um, and these are called binary relationships. And we will also model ternary, but anything more complex than that requires a little bit more, which is in a um, future section. So here we have an employee works for a department. Employee one, relationship one, department one. And this is all um, it's just conceptual. Okay, you don't put this in front of a user, and you certainly don't implement it. This just conceptually, though, you can see that there are three employees that work for Department One. You can just see the number of lines that converge on D1. Two employees work for D2. Two employees work for D3. So that's one, two, three, four, five, six, seven converging lines. And sure enough, we have seven employees, seven relationships because it's binary. Okay, now we start to see um, um, many to n, many to many, more or less relationships. You can have more. You got a lot of projects. You got a lot of employees, and now you have this more complex relationship where you have more, an employee can work on multiple projects, and a project has multiple employees that are working on it, a many to many relationship. Um, so we model that conceptually at first in a diagram, but then we'll figure out how to implement that in an actual real world database. So the relationship type um, is the description of the relationship, and it identifies how uh, uh, those entities relate or participate in the relationship. I don't use that term frequently when dealing with database customers, but that's what it is. Not every entity participates in every relationship, certainly. And you can put constraints on relationships. Uh, it could be that every employee has to have a relationship with a department. Every employee has to have a department number. You cannot have a null value. They can't be a free floating uh, um, employee. So uh, so we can model that. Um, so we got a diamond box. Now I'm used to just the straight line with the crow's feet on the end, just straight lines between entities. But in this traditional ER diagram format, you put what would be a decision point in a flow chart, a diamond symbol, but that's the name of the relationship or the relationship type. Um, it's not shown with an arrow, um, but it should be, for readability's sake, for the user to be able to use this, make it left to right. So an employee works on a project so that it makes grammatical sense. It also needs to make graphical sense. Yuck. Okay. Uh, so we have 6 relation types all listed here, and they're all binary. Um, we've got employee works for department, an employee manages a department, a department controls a project. So each project has to have a lead department. An employee also works on a project, doesn't work for a project. They work on a project. They work for a department. So that's where words count as far as, and it matters. We've got a section in the book names matter when it comes to classes and variables and attributes and methods and database columns and database tables and index names and all of that. Names matter, meaningful names, and a naming convention really help. So yeah, that's the rest of the relationships that we'll model in our diamonds. Yay! So now we have um, our more or less complete schema diagram. So we've got our entities in rectangles, the attributes of those entities in ovals, and how those entities relate and the cardinality, um, whether it's one or many or zero to many or one to many. Um, we have that all. Oh, and I'm seeing one derived attribute, number of employees. You would never want to store the number of employees for a department because it's going to change. You don't store dynamic data like that. You derive it whenever you need it, in my personal opinion, and in my professional experience. So there it is. Um, yeah. Uh, I don't know that there was ever an entity type that was refined into a relationship. I think we always had entities and relationships and attributes. So uh, your cardinality ratio, this matters, and can be implemented at the database level. It matters conceptually. It matters. uh, um, physically. One to one, generally speaking, we'll go through a process that's more down to the implementation level, normalization. Generally speaking, if there's a one to one ratio, it's not really a relationship, really. It's generally an attribute, but every once in a while you have something like that. One to many you see all the time, like employees to projects, employees to dependents. But then you have many to many. You have many employees, you have many projects, and and you'll have to figure out a way to implement that and constrain the database appropriately. And then there's existent dependency. So you can, have zero or optional participation in the relationship. Again, you don't frequently use this too much when talking just good old MySQL or Postgres or whatever, or one or more. So what that means is either you can have a null value or you can't. Like I said, an unassigned employee has to have, the initial data entry screen when an HR person is loading up an employee, they're going to have to pick a department. Sometimes when you don't know where they're going to be working, there will be a temporary department that is, maybe um, orientation. Their work for the orientation department. But you've got to pick one. That's a one or more um, participation constraint. But sometimes, like I work with an academic database that if you have not been assigned a um, a faculty advisor, which you don't have to have an advisor until you're, a sophomore, it's null. And you can find the people who have not been assigned a faculty advisor by looking for null values. So that needs to be modeled appropriately and it needs to be implemented appropriately. Sometimes it's okay to have a null value. Here's many to one. You've got uh, many employers, but they all work for a single department. Um, M to M again. Many employees can work on many projects, and projects can have many employees. Many to M to N, many to many. The N is like from one to infinity. And recursive relationship types, um, where you have like a supervisor column in an employee table, where you have every employee is listed as an entity, right? Every employee is a row, is an instance of that entity. But you'll also have, so they've got a key field, right? Employee number generally. But you can also have that person's supervisor. And there, generally speaking, would only be one that is null, and that's the company president. Everybody else has the employee number of their supervisor in the supervisor employee number column, and uh, that self-referencing um, recursive relationship is something that you can model. It's something that you can implement in the database, and it's something that you can execute with like a SQL query or where you can go grab someone's supervisor's information. Okay, so an employee uh, can be an employee, but they're also a boss. So you could determine all of the supervisors, and you can count the number of people that they supervise. You wouldn't store that. Um, so there you go. Um, and the recursive relationship type, it's got to point uh, back to the same entity. So here's the um, whether or not the participation diagram. But here's how we model it. This is closer to what I'm used to. So you have an employee, but then we have this relationship, supervisor to supervisee. Um, a supervisor can supervise n employees, but a an employee can only have one supervisor. So this diamond of supervision is a recursive relationship. It's not stored. It's not a separate entity. It's a recursive relationship. Okay. Weak entity types, yeah, don't have uh, um, a key, and you model it, but you would rarely ever have something like this. Um, I almost to the point where I'm like, you can model this conceptually, but I don't know that you would ever implement it. Weak entity type has no key that depends on another entity type. So um, it could be sitting out there with no relationship. Could just be lookup data, reference data that has no specific relationship to anything in your mini world or your ER diagram. Yeah, conceptually, dependent would be a weak entity type, but you wouldn't implement it that way. But you can model it that way on your diagram. So a dependent, yeah, is a dependent of an employee. Um, so relation types can have attributes, but that's where we start to get into, uh, like I said, the employee project relationship starts to get to be a many to many relationship that you would break out into its own entity, an employee project entity. So I don't want to get going too much into this, but it can be for this modeling type, for this conceptual diagram, a relationship can have attributes. There are things that you can store about that relationship, which inherently makes them entities. So there you go. Um, so yeah, we're showing the number of hours now as an attribute of works on. Um, which, yeah, conceptually, there you go. And back in the requirements, we were modeling the start date of a of a manager's oversight of a department. So we've got start date, which is an attribute of the works on or of the manager's relationship, which is kind of counterintuitive. But there you go. It's a conceptual model. This is just to get things documented um, down to your stakeholders and your database designers. Someone would take this and actually make an implementation model. Um, Constraints on the relationship. We've got the cardinality and the participation constraint, whether or not it's zero to many or one to many. Cardinality ratio and participation constraint. Um, and yeah, you can uh, you can model the min and max. I beg your pardon. Um, the participation in a relationship, which is just like I said, whether or not an employee um, has to work a minimum of three projects or, has to be work, has to work on one project, whether or not they have to be in a department, those sorts of participating in the relationship. It to me, it's very well linked to the cardinality ratio, but there you go. Um, yeah, a zero or one, an employee manages a department. Either they do or they don't. And again, this is notation. Um, uh, but a department manages a project, so that would be one and one. So there's a couple of examples of the relationship structural constraint. How many uh, entities relate on either side of the relationship? Okay. So here is our updated ER diagram. Now we're really starting to show um, the 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 relationship constraint and the attributes constraints on the relationship, and that'll eventually get modeled into something that's implementable in the database. These relationships, generally speaking, uh, get modeled in the database as opposed to this differently when we move forward in our diagramming. But UML is another format, and then I think it's next week we talk about enhanced entity relationship diagrams. Uh, we may skip a chapter. But again, I'm used to using the one that you diagram um, out of Workbench with crow's feet annotation. Last time I looked it up, I think that was an ANSI standard. And there's our cheat sheet again. And UML is a more of an object modeling language, so it's equally interested in data and functionality. But we're going to go into this in a different section. But for example, um, I like this um, um, format better, where the attributes are actually listed in the box. The box is an entity, um, and um, the individual attributes are for that entity are in the rectangle. It starts to look closer to data that you would store, like the start date of a manager managing a department. That's going to have to be modeled as a table. Each one of these equates to a relational database table, which uh, to me starts to be a little less conceptual and weird looking, and something I can actually do something with, something useful. And then, yeah, other alternative diagrammatic notations. Um, I'm used to uh, D cardinality ratios. I'm used to those and you don't name a relationship. You just diagram the data. So two's binary, three's ternary, and then it gets uh, kind of weird after that. So there's an example of a ternary relationship, um, and then even higher than that, you start to get um, It's implementable in the database, but it gets to be um, fairly complex. And here's another example of a ternary relationship versus binary. Okay. In our university database, this is what we're dealing with um, in the sample database that you will implement in MySQL. And there's the diagram for it. Students, instructors, colleges, um, and the relationships between them. Each uh, department will have a chair person, um, which will be an instructor. Every college has a dean, which will also be an instructor. Um, a department has students. A department offers courses. Courses will be um, broken into sections. An instructor teaches a section. So all standard. I don't see any compound attributes, composite attributes. Nope. Good. They're bad practice. Okay. So yeah, conceptually modeling, and we'll get much more concrete in future lectures. Uh, so I look forward to seeing you in the discussion board. Have a good week.